Welcome to homework.
So here in this problem we are given that helium gas is compressed from pressure P1 90 kilopascal, temperature T1 30 degrees Celsius to the final pressure P2 as 450 kilopascal, and the process is a reversible adiabatic process. So we can say that reversible adiabatic means isentropic process. That means the entropy remains constant. And our aim is to calculate the final temperature and the work done during the process. And in the A part we have to assume that it's a piston cylinder device, and in the B part we have to assume that it compressed by the steady flow compressor. So first of all we'll be solving the A part, and the specific heat at constant volume CV, it is 3.1156 kilojoule over kg Kelvin. This value is for helium gas, and we have obtained this value from uh, table A2. And similarly Cp will be 5.1926 kilojoule over kg Kelvin, and the value of K, that is the heat ratio, the specific heat ratio, will be 1.667, and we have all obtained all these values from the table A2. Now the final temperature T2, we can get it from the isentropic relation, that is T2 will be equals to T1 times P2 divided by P1 to the power K minus 1 divided by K. So we have all the values here, we can plug it here. So T2 we have 303 Kelvin times P2 divided by P1. So P2 we have 450 kilopascal divided by P1 is 90 kilopascal to the power K minus 1. So K minus 1 will become 0.667 divided by K is 1.667. So after solving this, we'll get the value of T2 as nearly 576.9 Kelvin. So this is the value of T2. Now next we'll be calculating the work input. So the work input, uh, we'll get this expression as m times u2 minus u1, and we've obtained this expression by using the energy balance equation, that is energy in minus energy out is equals to change in energy of the system. And since there is no energy out, so E out is 0, and the change in energy of the system will be change in internal energy, and we can write this expression as it is, and it will be mcv T2 minus T1. So we have all the values here, we can plug it here. M we have given in the equation, it is not given, yeah, it is not given, so we can take it as 1, or we can divide this expression with m. So we'll get the unit of work input as kilojoule per kg. So CV, so we can divide this thing as divide by m. So CV we have 3.1156 kilojoule over kg Kelvin times T2 we have 576.9 Kelvin minus T1 we have 303 Kelvin, because if we convert 30 degrees Celsius into Kelvin we'll get 303 Kelvin. So after solving this we'll get the value of work input as it's 853.4 kilojoule over kg. So this is the work input. So this is the answer for the A part. Now next I will be solving the B part of the problem. So in the B part we have to find the final temperature and the work input. So final temperature will remain the same, that is T2 that we have obtained in the last part. T2 will be 576.9 Kelvin, but the work input will be changing in this part. So for that, to calculate this the work input, we will be using the energy balance equation, that is energy in minus energy out is equals to change in energy of the system. Since this time the system is steady flow compressor, so change in internal energy of the system will be 0. So we can say that energy in will be equals to energy out. So energy in we have the work input plus it's H1, and it will be equals to H2. From here the work input will be H2 minus H1. So we have H2 minus H1 is Cp T2 minus T1. So Cp we have 5.1926 kilojoule over kg Kelvin times T2 minus T1. So T2 we have 576.9 Kelvin minus T1 we have 303 Kelvin. So after solving this, we'll get the value of work input as nearly 1422.3 kilojoule over kg. So this is the work input in case the system is steady flow compressor. This is for compressor, and the work input for piston cylinder device, it was 853.4 kilojoule per kg. So I hope you got both the part. I thank you so much.